All right, so the next unit we're doing is going to be topic 3.4, which is differentiating inverse trig functions. So we will focus on taking derivatives of 6 inverse functions. So like I told you guys in class, the ones that you truly have to memorize are these 4 right here, okay? And these 2, they will be on homework assignments, but they will not be um, given on any tests. Uh, This green box over here is going to be the derivatives of basic inverse trig functions. That means when the stuff that's inside the trig function is just x. And when that happens, when you're solving for this u prime right here, that's just going to be 1 because the derivative of x is just going to be 1. So why does this work? So we kind of started talking about this in class. Let's find dy dx. But we're going to use we're going to rewrite this first or use implicit differentiation in order to do this. But before we do that, to eliminate, one way that we can rewrite this so that it's not in terms of inverse trig is that we can take the sine of both sides. And if you guys remember that the sine of arc sine of x is just going to be x. So sine of y is equal to x. And the reason that this is important is because it is giving us our ratio that for the angle y, the opposite, because sine is so, right, from SOHCAHTOA, the opposite is going to be equal to, so O over H for the angle y is going to be x over 1. So you got to keep this in mind. This is where we're taking it to kind of figure out the triangle and why it's important to figure out the triangle in just a second. So now that we have our function in terms of the regular trig function or implicitly deriving, right? We are going to derive both sides of this equation, but we're going to find dy dx. So we're deriving sine of y with respect to x. So the derivative of sine of y is going to be cosine of y times dy dx. And that is going to be equal to 1. And of course, when you solve for dy dx, you end up with 1 over cosine of y. Now, where did this come from, right? Why can't we just leave it as cosine of y? Well, the formula is in terms of x because our inverse trig function is in terms of x. So in order to figure out where that square root of 1 minus x squared came from, we are going to use this triangle. And we're going to use the information that came from the original problem right here. And remember this y? Well, this y is going to be the angle of this triangle. And usually on the unit circle, right, the angle is made between the x and the hypotenuse. So this is angle y, we're going to call it. And according to this, the sine of this angle y is opposite over hypotenuse, which is x over 1. Now, to figure out this problem, we got to figure out what is cosine of y. And of course, we can do that using the Pythagorean theorem. So this tells us that x squared plus our unknown term squared, right, is equal to 1 squared. So once you solve this, and the reason we got to figure out what the cosine is the adjacent leg. So we're trying to figure out the adjacent leg. So once you solve this, you end up with adjacent leg squared is equal to 1 minus x squared. And then you take the square root. And so the adjacent leg is going to be equal to the square root of 1 minus x squared. Now we're going to stick to quadrant 1 on this. I know it doesn't look like it's in quadrant 1. That's why in class I said let's flip it. So that means this side right here is equivalent to 1 to the square root of 1 minus x squared. So now when I ask you what is cosine of y using this triangle, well, 1 cosine of y is the adjacent leg, which is the square root of 1 minus x squared, over the hypotenuse, so over 1. But of course, we don't write the over 1. And that is how these formulas came to be. They all got derived from the trig ratios using the triangle and rewriting it in terms of x. So the long method for deriving inverse trig would be to do what we just did, right? Take sine of both sides. And then when you do that, you got sine of y equals 2x. You're going to implicitly derive. So you get the derivative of sine of y, which is cosine of y times dy dx. And the derivative of 2x is 2. And then you would solve for 2 over cosine of y. And you have to draw your triangle to figure out what this bottom is. The shortcut is to use the inverse trig rules. So the derivative of arctan is going to be u prime over 1 plus u squared. So in this case, u is 3x. So the derivative of arctan of x is going to be u prime, so it's the derivative of u over 1 plus u squared. When you solve that, you got 3 over 1 plus 9x squared. And that's our derivative. As we keep going here, so remember that this means the same thing as arctan of x to the half. So in this case, our u is x to the half. So the inverse trig rule says that the derivative of arctan of inverse tangent is going to be equal to x to the half derived over 1 plus x to the half squared. And once you clean that up, the derivative of x to the half is going to be 1 half x to the negative 1 half, which we'll clean that up in just a second. All of that over 1 plus x, because 1 half times 2 is going to be 1. So 1 plus x. Now remember, you cannot have negative exponents. So just to kind of make things look a little bit neater, what I'm going to do is I'm going to write this negative half, x to the negative half over 2. And all of that is going to be divided by 1 plus x. So when this moves to the denominator of with 2, you've got 1 over 2 square root of x. And all of that is over 1 plus x. But we can't have double derivatives. So what we're going to do is flip the guy and multiply. So the answer here ends up being 1 over 2 square root of x times 1 plus x. And you would leave it just like this. If you wanted to simplify it a little bit more, you could, but that's a sufficient answer. All right, example D is arc secant of this stuff e to the 2x. So the u that's in here is e to the 2x. Let's keep that in mind. But this whole thing is squared. So this actually needs the chain rule first, then inverse trig derivatives. So when it says chain rule first, I'm first gonna bring down that 2. Everything on the inside is gonna stay the same. Raised to the 1, right? Times the derivative of the stuff on the inside. So times the derivative of e to the 2x. So I need to derive this part. So the 2 already got derived, or the stuff squared already got derived. So of course this is going to come along for the ride. And then the derivative of inverse secant, going back to our table, is u prime over absolute value of u times the square root of u squared minus 1. So remembering that u in there was e to the 2x. So it's going to be u prime, so e to the 2x, the derivative of that, over absolute value of e to the 2x times the square root of 1 minus, or sorry, u squared minus 1, which is e to the 2x squared minus 1. And now I got to derive this part. So this is again going to come along for the ride. The derivative of e to the 2x is e to the 2x times 2. And all of that is going to be over e to the 2x times the square root of e to the 4x minus 1. So if this was a short answer or FRQ, you would leave it just like this, okay? Don't go any further. But one thing we have to notice when it comes to absolute values, is this absolute value necessary when you have e to the 2x? What is, if you were to plug in a negative number into e to the 2x, will this ever be negative? Will this whole entire thing ever be negative? And the answer is no. Because even if you plugged in a positive 1, it's e squared. If you plugged in a negative 1, it's 1 over e squared. It will always be a positive answer. And when that happens, we have to understand that the answer does not necessarily need the absolute values. And sometimes if they give you these types of problems with absolute values, the multiple choice answer might have a missing absolute value. And you might think to yourself that you've done something wrong. But there is some thought that goes into why they eliminated the absolute value. And the reason in this case it's important to eliminate the absolute value is because there's an e to the 2x on top that will divide out with the e to the 2x on the bottom. So the answer is now going to be 2 times 2, which is 4 secant of inverse secant of e to the 2x. All of that is over the square root of e to the 4x minus 1. And that's our derivative. So that was a lot. to take in, right? In one problem. So if you need to stop it and rewatch this video, please go ahead and do that. All right, the last section, 3.6, is calculating higher order derivatives. For the most part, nothing new is going to be learned here. The only thing that we are going to add is this terminology. So when we have an f of x function in a story problem that is about moving objects or particles or cars, whatever it is, we call that, or the original function is called the position function because it gives you the position of the ball at a specific time, right? Now, if you take the derivative of the position function, you actually have velocity. And if you take the second derivative of the position function, aka the derivative of velocity, you will obtain the acceleration function. So you will be able to figure out what is the velocity at 2 minutes. What is the acceleration at 2 minutes? Okay. So we'll come to that in just a sec. So some common higher order derivative notations, we kind of went over these in class. You got y prime, y double prime, y triple prime. And then after that, they just start writing numbers instead of writing 4 commas. The nth derivative is y to the n. Another form is they might write it f prime of x, f double prime of x, f triple prime, f fourth prime of x, and so on. And then, of course, there's this. This is the Leibniz notation, it's called. Leibniz, I don't know if I'm spelling it right, but you got the second derivative, third derivative, fourth derivative, and on and so forth. So, example 1 says find the second derivative of this original function. So in order to find the second derivative, you first have to find the first derivative. And that's going to be 6x squared uh, plus sine of x plus 1 over x minus e to the x. And now the second derivative is 12x squared plus cosine of x minus 1 over x squared minus e to the x. I know I did this part pretty quick, but if you remember, a little side note, in my head, I rewrote it as x to the negative 1, brought down the negative 1, and this became negative 1 x to the negative 2, and this is that derivative, okay? All right, back to the Burj Khalifa. Let's revisit a scenario from our first week of class. We didn't do these notes the first week of class, so don't worry about it too much. Suppose a ball is dropped from the top of the story of the Burj Khalifa in Dubai, 2,717 feet from the ground. The position equation that depicts the height in feet is given by S of t. The ball is from the ground at time t in seconds. So the time is seconds. S of t is going to be represented by feet. First part, compute the velocity. So they said compute velocity when t equals 5. So when we want to compute velocity, we want to take the derivative of s of t. That will give us our velocity function. And the derivative is going to be a negative 32 t minus 10. And now that I have my velocity function, I can plug in 5. And I'll let you guys do the math. Next up, we want to compute the acceleration. So acceleration is obviously the second derivative of position, or it's the derivative of velocity since we already solved velocity right here. So I can just take the derivative of this, and that will give us our acceleration, which is negative 32. So what is the acceleration at 5 seconds? Well, it's going to be negative 32 feet per second squared. And of course, the units on velocity is going to be feet per second. When will the ball hit the ground? Which function are we going to be using to answer that question? So the ball hitting the ground, that means its position, aka S of t, aka the y value, is going to be equal to 0. So we're using the position function, which is negative 16t squared minus 10t plus 2,717, and we're going to set that equal to 0. And you see that this is a quadratic equation. So with a quadratic equation, when it's set equal to 0, we could factor it, right? But this is a calculator-based question. So you got to find the zeros. Find the zeros on your calculator. I'll let you guys take that time to do that. And you're going to get 2 zeros. One of them will make sense and the other one will not make sense. So find the 2 times where this function is equivalent to 0 and tell me which one works. Now, what will the velocity of the ball be at impact with the ground? So in order to answer this question, you have to do part C first, because part C is going to give you the time when this thing hits the ground. So once you figure out when it hits the ground, well, you can take that answer that came from here and you plug it into the velocity function that we solved for in part A, and it should give you your answer in feet per second. All right, so here is example 3. Example 3 is uh because the moon has no atmosphere, a falling object on the moon encounters no air resistance. So that's going to be maybe important. In 1971, David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is given by this. So this is our important function where S of t is the height in meters and t is the time in seconds. What is the ratio of the Earth's gravitational force um, the Earth's gravitational force to that of the moon? So there's some information here that is missing, right? When they're asking for the gravitational force, the ratio of the gravitational force, you want to get to acceleration. So you have your S of t, you got to take that derivative for the moon. So this is the moon stuff. So you take that derivative and you end up with negative 1.6 t, but you need the gravitational force, which is the acceleration, and the acceleration is going to be negative 1.6. Now, they didn't give us the position function for the falling objects on Earth. But I do know that gravity on Earth or the acceleration at time t of any object on Earth is negative 9.8 uh negative 9.8 meters per second. In the last example, it was negative 32 feet per second. This one's going to be the answer in meters. So once we have both, we know that this is negative 9.8 meters per second. We know this is negative 1.6 meters per second. So the ratio of the Earth to the moon is going to be negative 9.8 over negative 1.6. That's our ratio. So you would get an answer here. I don't know what the answer is. And that will tell you how the Earth's gravity uh, is stronger than that of the moon by how much. I'll let you guys figure that out, or you can scan this QR code to see his answer. Um, a challenging second derivative. I'm going to leave this one for you guys. It's not something that we often see. No, actually, it is. It is. Because it's not that challenging, right? You know that the derivative of cosecant of x is going to be negative cosecant of x cotangent of x. So then the second derivative, I'll let you guys do that, of the first derivative is you have to use the product rule. So we're going to use the product rule to figure out this derivative. And then clean it up if you can. So I will leave you guys with that. The product rule here are the two products. So you take the first guy as is, right? Times the derivative of cotangent of x plus cotangent of x times the derivative of negative cosecant of x. So I'll let you guys finish up that problem. All right, I don't know why I'm missing example 5 here. There should be one more example. We'll do that in class. All right, good luck.